You were standing in the dark on a mountaintop in Chile, your eye pressed to the eyepiece of a telescope, watching a pale smear of light called a galaxy spin slowly against the black. The air is cold and thin. The stars do not twinkle up here at this altitude. They sit still and sharp, like pins pushed into black velvet, and that pale smear of a galaxy rotates so gently you almost wonder if you are imagining the motion. That smudge of light is held together by something that has no name most people remember and no face anyone has ever seen. Dark matter. It is not a star, not a planet, not a cloud of gas. It is something else entirely, something that fills the spaces between the stars and pulls on everything with a gravity that no telescope has ever been able to photograph. What is at stake is whether the universe we see is the whole universe or just a thin skin stretched over something vast and invisible. And understanding this hidden thing will change how every person on Earth thinks about the night sky. If you want to be in the room when the next piece of this puzzle drops, put your name on the notification list for this channel so the next video finds you before you have to go looking for it. The galaxy you are watching is not unusual. There are roughly 2 trillion galaxies across the observable universe, and almost every one spins too fast for its visible matter to hold together. The stars at the edges should fly off like children flung from a spinning ride, but they do not. They stay. They orbit in calm circles. They behave as if something massive and invisible is gripping them from the outside. For decades, that something was treated as a ghost in the machinery of physics. Scientists could measure its pull, but could not find its body. They gave it a placeholder name and moved on, hoping the right instrument would come along. That instrument now exists, and what it has found is sending quiet shockwaves through the entire field of astronomy. The ghost is no longer just a ghost. It is starting to come into focus, and what the focus reveals is stranger than anyone expected. To see why this matters, we need to step back. Most people who have heard of dark matter believe it is just a theory, a mathematical patch scientists slapped onto their equations when the numbers did not add up. The story goes that astronomers noticed galaxies spinning too fast, got confused, and invented an invisible substance to fix the problem, rather than admit their models might be broken. That is the version most textbooks still lean on, and it is the version most people carry in their heads when they hear the words dark matter. The story really begins in the 1960s and 70s, in a small office at the Carnegie Institution for Science in Washington, where a woman named Vera Rubin was doing something almost no one else thought was worth doing. She was measuring how fast stars orbit inside galaxies. Not the bright stars near the glowing center where most astronomers pointed their telescopes. The faint stars at the very edges, the ones so far out they barely registered on the photographic plates she was using to track them night after night, year after year. The work was slow, tedious, and unglamorous. Most of her colleagues thought she was wasting her time on a problem that had already been solved. Rubin was not a famous scientist at that point in her career. She had been turned down by Princeton for graduate study because they did not accept women into their astronomy program at that time. She had been told, politely but firmly, that astronomy was not a suitable field for mothers. She had persisted anyway, earning her doctorate from Georgetown University in 1954 by completing her coursework while pregnant with her second child. She raised 4 children and did her calculations on napkins and the backs of envelopes while her kids slept in the next room. Then she drove to the observatory at night and measured starlight, one galaxy at a time, building a data set that nobody had bothered to build before her. Her persistence was quiet but relentless, the kind that does not make for dramatic stories but eventually changes everything. The technique she used was simple in principle, even if it was exhausting in practice. When a star moves toward you, its light shifts slightly toward the blue end of the color spectrum. When it moves away from you, the light shifts toward the red. By measuring exactly how much the light has shifted, you can calculate how fast the star is moving along your line of sight. Rubin and her collaborator Kent Ford, who also worked at the Carnegie Institution, had built a special spectrograph, a device that splits light into its component colors so shifts can be measured precisely. They attached this instrument to some of the largest telescopes in the world and pointed it at dozens of galaxies, carefully mapping the speed of stars at different distances from the center of each one. What they found did not match any model that existed at the time. In a normal gravitational system, the material closest to the center moves fastest, and the material on the outside moves slowest. Think of a figure skater spinning with their arms pulled tight against their body, then extending their arms outward and slowing down as a result. That is how gravity is supposed to work. The farther you get from the center of mass, the weaker the pull, and the slower the orbit should be. You can see this same pattern in our own solar system. Mercury, close to the Sun, zips around in just 88 days. Neptune, far out at the edge, takes 165 years to complete a single orbit. The pattern is clear and consistent. But the galaxies Rubin measured did not follow that rule at all. The stars at the outer edges were moving just as fast as the stars near the middle. The rotation curves, as astronomers call these speed maps, were flat. They did not dip at the edges. They did not taper off the way solar system orbits do. They just kept going, fast and steady, all the way to the visible edge of each galaxy, as if something unseen was holding the outer stars in place and refusing to let them slow down. It was as if you watched a merry-go-round spinning and noticed that the horses on the outside rim were moving just as fast as the horses in the center, which is not how merry-go-rounds work unless something invisible is pushing them. Rubin published her results in a landmark paper in the Astrophysical Journal in 1978, co-authored with W. Kent Ford and Norbert Thonard. The paper was careful and quiet in its tone. It did not make grand claims or demand attention. It simply presented the data from 21 galaxies and noted, in the plainest possible language, that the visible matter inside these galaxies could not explain the observed speeds of the outer stars. Something else was there, something heavy, something invisible. The paper did not use the phrase dark matter prominently. It let the numbers speak for themselves. The reaction from the astronomy community was not immediate excitement. It was skepticism, and in some corners, open resistance. Some researchers proposed that the galaxies might contain far more ordinary matter than anyone had estimated, hiding in the form of very dim stars or cold gas clouds that the telescopes of the 1970s could not easily detect. Others suggested a more radical idea, that the laws of gravity themselves might need to be adjusted at very large cosmic distances, an approach later given the name modified Newtonian dynamics. A few senior astronomers dismissed the data entirely, suggesting quietly that Rubin's measurements were not precise enough to support such an extraordinary claim, and that her reputation was not enough to overturn decades of accepted physics. The 1970s and 80s were a time when physics seemed focused on more dramatic discoveries. Particle physicists were finding new subatomic particles almost every year. Cosmologists were debating the Big Bang theory. Dark matter, by comparison, seemed like a dull problem that offered no clues about what it actually was. But Rubin kept measuring. Galaxy after galaxy produced the same flat curves. The Andromeda galaxy, our nearest large neighbor, showed the same pattern. Small spiral galaxies showed it. Large elliptical galaxies showed it. Other research teams eventually confirmed her results using different instruments, different wavelengths of light, and different methods of analysis. By the late 1980s, the evidence had become simply too large to ignore. Galaxies across the observable universe were rotating too fast for their visible matter to explain, and the only explanation that fit the data without breaking other well-tested areas of physics was the presence of a massive, invisible substance surrounding every galaxy, like a silent, unseen halo. The assumption hardened into something that felt like fact over the following decades. Dark matter was real, but it was also untouchable, invisible, and fundamentally impossible to study directly with any instrument that existed. It was a ghost you could measure through its gravitational pull, but never see with your own eyes or capture in a photograph. The best anyone could do was map its effects from a distance and hope that someday, somewhere, a new tool would arrive that could peer deeper into the darkness than anything that had come before. The textbooks began to reflect this settled view. Introductory astronomy courses taught dark matter as a fact, not a hypothesis. Roughly 85% of all the matter in the universe is dark matter. Only about 15% is the ordinary stuff that makes up stars, planets, and people. When you combined dark matter with dark energy, an even more mysterious force that pushes the universe apart, the picture that emerged was one in which everything we can see and touch accounts for roughly 5% of the total content of the cosmos. The rest is invisible. The rest is unknown. And for a long time, it seemed like it might stay that way forever. In your living room right now, a thin haze of dark matter is passing through the walls, the furniture, your body, without touching a single atom of any of it. It does not interact with light. It does not interact with ordinary matter in any way we can detect at close range. It only pulls. It only exerts gravity. And for roughly half a century, that single lonely fact was all anyone could say about it with any real confidence. Dark matter was real. Dark matter was everywhere. And dark matter was, for all practical purposes, a mystery that might never be solved. What we have just taken for granted turns out to be a small part of a much larger story. The assumption that dark matter could only be studied indirectly, that it would forever remain a ghost visible only through its gravity, has just been cracked open by a telescope that sits 1 million miles from Earth and sees light that has been traveling since before our solar system formed. The next act of this story is about what that telescope actually saw when it looked into the dark. Drop a comment below describing the exact moment you realize the invisible thing holding galaxies together might be real instead of just a theory, because reading those moments helps us shape what this channel investigates next and which mysteries we dig into first. Months after the James Webb Space Telescope began its science operations in 2022, a team of astronomers pointed it at a cluster of galaxies called SMACS 0723. This cluster sits roughly 4 billion light-years away from Earth, and it is so massive that its gravity bends the light of even more distant galaxies behind it, acting like a giant magnifying glass floating in the vast darkness of intergalactic space. The researchers who requested these observations were not hunting for dark matter that day. They were running one of the first deep-field tests of the telescope's ability to see faint, distant galaxies whose light had been magnified and stretched by the cluster's gravitational lens, a process where extremely heavy objects bend the path of light around them the way a glass lens bends the light from a lamp on your bedside table. What the team found when the images came back was not what anyone expected. The lensing patterns in the background galaxies were not smooth and even, the way standard models predicted they should be if the cluster's mass were spread uniformly through space. Instead, the background light was being bent in uneven, irregular ways that suggested dense clumps of mass sitting in places where no visible matter existed at all. It was the kind of distortion you would expect if dark matter were not distributed smoothly, but was instead piled up in specific knots and threads, like lint caught in the weave of a fabric. The difference between the predicted smooth lensing and the observed clumpy lensing was like the difference between a calm pond reflecting the sky perfectly and a pond where invisible stones have been dropped beneath the surface, rippling the reflection in ways you cannot explain. The team that made this observation spent months analyzing the lensing patterns before they were confident enough to publish. They ran computer simulations of what the cluster should look like under different dark matter distributions, comparing the simulated lensing to what James Webb had actually recorded. In simulation after simulation, a smooth dark matter halo produced smooth lensing. Only when they introduced clumps and filaments into their dark matter models did the simulated patterns begin to match what the telescope had seen. It was not a single anomaly. It was a systematic mismatch between the old models and the new data, the kind of mismatch that forces an entire field to stop and reconsider assumptions that had been treated as solid for decades. Then in 2023, a separate team led by astronomers at the University of Toronto turned James Webb toward a very different kind of target, a galaxy called Dragonfly 44. This galaxy is an ultra-diffuse galaxy, meaning it is extremely faint and spread out across such a large area of sky that it had been nearly invisible to every telescope that had ever looked in its direction before. If you held up a piece of tracing paper in front of a window on a cloudy day, the faint glow you would see through the paper is roughly what Dragonfly 44 looks like through even a large telescope. The expectation going into the observation was straightforward and conservative. Dragonfly 44 had already been tentatively identified as a candidate dark matter galaxy, a place where almost all the mass was thought to be invisible rather than shining as stars. James Webb, with its vastly superior sensitivity, should simply confirm that basic picture. That is exactly what the telescope found, but the precision of the measurement was staggering in a way that surprised even the researchers who made it. The team, publishing their results in a 2023 paper in the Astrophysical Journal, determined that Dragonfly 44 is 99.99% dark matter by mass. The visible stars in the galaxy account for roughly 1/10,000th of its total weight. Everything else, almost the entire mass of the galaxy, is something you cannot see. The gap between what was expected and what was found was not just a simple confirmation of an old idea. It was a confirmation delivered at a level of numerical precision that made the invisible substance feel almost tangible, the way a highly detailed map of ocean currents drawn from satellite data can make the water itself feel more real, even when you are standing on dry land hundreds of miles from the nearest coast. The lead researcher later described the moment the numbers came in during a public lecture. The team had expected a high dark matter fraction, maybe 90 or 95%, but when the data pointed to 99.99%, the room went quiet for a long moment. The number was so extreme it felt less like a measurement and more like a statement about the universe itself. Soon after that result was published, Another research group turned James Webb toward the very early universe, targeting galaxies that existed when the cosmos was only a few 100 million years old. These were among the very first galaxies ever formed, born in a universe that was still hot and dense and chaotic compared to the calm, cold spread of space we see today. The standard models of dark matter made a clear and specific prediction about what these infant galaxies should look like. Dark matter was thought to form large, smooth, rounded halos first, filling enormous volumes of space with an invisible scaffolding, and then slowly draw ordinary matter inward to build galaxies on top of those halos, like houses built on invisible foundations that were laid down before the construction ever began. The telescope found something different. The early galaxies were smaller, denser, and far more numerous than the models had predicted they should be at that epoch. They were packed tightly with stars and seemed to sit inside dark matter clumps that were much smaller and much lumpier than the smooth, expansive halos the models described. The difference between the predicted smooth foundations and the observed lumpy clumps was like the difference between a freshly poured concrete slab and a field of boulders dumped in the same spot. The universe in its youth did not look smooth and orderly. It looked rough and uneven, as if dark matter had clumped together in dense knots from the very beginning, like rain hitting a window and running in uneven streams. Other teams using James Webb soon reported similar findings in different parts of the early universe. A group at Yale University found that galaxies in a region called the Pandora cluster showed the same kind of unexpected lumpiness in their dark matter distribution. A Japanese team observing a field near the constellation Fornax found dense knots of dark matter in areas where the smooth halo models predicted nothing should be there. The pattern was repeating itself across different instruments, different research groups, and different parts of the sky, which made it increasingly difficult to dismiss as a measurement error or a processing artifact. At this point in the story, it is worth pausing to say honestly that not every researcher agrees on what these early galaxy observations mean. Some astronomers have argued that the data from such extremely distant objects might be affected by measurement uncertainties that are difficult to quantify, or that the theoretical models simply need calibration and refinement rather than a fundamental overhaul. A paper published in early 2024 by a team at the University of Cambridge suggested that some of the apparent lumpiness in the early dark matter distribution could be an artifact of how the telescope's images are processed, calibrated, and interpreted, not a genuine feature of the dark matter itself. The science here is not settled. The debate among experts is real, and it is healthy, and it is ongoing. But what is not in dispute is that James Webb is seeing structure in the dark matter distribution that no earlier telescope had the resolution to detect, and that the structure it sees does not neatly match what most of the leading models predicted. In parallel with the early galaxy work, James Webb has been making a different kind of measurement that connects even more directly to Vera Rubin's original discovery from half a century earlier. The telescope has been measuring the rotation speeds of individual distant galaxies using a spectroscopic technique very similar to the one Rubin pioneered in the 1970s, but now applied to galaxies so far away that their light has taken most of the age of the universe to reach us. A 2024 study led by researchers at the Max Planck Institute for Extraterrestrial Physics in Germany used James Webb to measure rotation curves in galaxies at redshifts around 2, meaning we see them as they existed roughly 10 billion years ago, when the universe was less than a third of its current age, and the Earth did not yet exist. The expectation going into this particular measurement was that these ancient galaxies might rotate differently from the galaxies we see nearby today, because dark matter halos in the early universe were thought to be less organized, less settled, and more turbulent than the stable, well-ordered structures we see surrounding modern galaxies. But the rotation curves came back flat, just like Rubin's galaxies, just like the galaxies in your local neighborhood of space. The stars at the outer edges of these 10-billion-year-old galaxies were moving just as fast as the stars near their centers, and the flatness of the curves implied that dark matter halos were already well-formed and well-organized when the universe was only a few billion years old. The surprise was not that dark matter existed at that early time, since the models always predicted it would. The surprise was that it was already behaving exactly the same way it behaves today. Like finding a river that has been flowing in the same channel for 10 billion years without ever changing its course or overflowing its banks. When the Max Planck team published their rotation curve results, the paper included a direct comparison to Vera Rubin's original 1978 data. The shapes of the curves were nearly identical, the same flat line, the same refusal to dip at the edges. The only difference was the distance. Rubin's galaxies were a few dozen to a few hundred million light-years away. The James Webb galaxies were 10 billion light-years away. The fact that the same pattern appeared at both distances, separated by most of the history of the universe, told researchers something important. Whatever dark matter is, it has been doing its job in the same way for a very long time. It is not a temporary phase or a transitional state. It is a permanent feature of the universe, as reliable as gravity itself. And here is where this stops being about one telescope and begins being about us. If dark matter has been shaping the universe in the same way for 10 billion years, then it is not a footnote in physics. It is the architecture beneath everything. The ground beneath your feet, the atoms in your body, the light that warms your face on a clear morning, all of it exists in the shape it does because dark matter pulled the raw material of the cosmos into patterns that produced stars, planets, and people. Understanding it is understanding the foundation of the house you live in. Send this video to a friend who still thinks dark matter is just a guess, because watching their expression shift at the Dragonfly 44 number is worth the 30 seconds it takes to forward a link and start a real conversation. What changes now is the pace of discovery itself. Before James Webb, dark matter research moved slowly because the evidence was indirect and the measurements were rough. You could weigh a dark matter halo approximately, the way you might guess the weight of a closed box by shaking it and listening to what moves inside, but you could not open the box and see what was in there. James Webb has changed that equation by making the measurements sharp enough to reveal texture and structure within the dark matter itself. The lumps in the SMACS cluster, the extreme purity of Dragonfly 44, the flat rotation curves at 10 billion light-years distance. These are not vague hints or suggestive patterns. They are high-resolution maps of something that was previously considered unmappable. 3 specific missions are now being planned or refined to follow up on what James Webb has started, and each one is designed to push the mapping of dark matter to a level of detail that would have seemed impossible even 5 years ago. The European Space Agency's Euclid mission, which launched in July of 2023, is currently scanning a third of the entire sky to build the largest three-dimensional map of dark matter distribution ever attempted. Euclid does not look at individual galaxies the way James Webb does. Instead, it surveys millions of galaxies at once, measuring the tiny distortions in their shapes caused by dark matter bending their light. The sheer volume of data it will produce over its 6-year mission will allow astronomers to see the large-scale structure of dark matter across billions of light-years, revealing the cosmic web of filaments and voids that dark matter has woven through space. The Nancy Grace Roman Space Telescope, scheduled for launch by May of 2027, will take this approach even further. Roman carries a wide-field camera that can capture images covering an area of sky 100 times larger than James Webb can see at one time. It will use this enormous field of view to measure weak gravitational lensing across thousands of square degrees of sky, detecting dark matter structures that are far too subtle and too large for any current instrument to map. The Roman telescope is not designed to study individual dark matter clumps. It is designed to map the entire dark matter forest, seeing the big picture in a way that no telescope has ever done before. And on the ground, the Vera C. Rubin Observatory in Chile, named after the same Vera Rubin whose flat rotation curves started this whole story half a century ago, is expected to begin full science operations in early 2025. The Rubin Observatory carries the largest digital camera ever built, a 3.2 gigapixel instrument that will image the entire visible sky every few nights for a full decade. Each image it takes will capture the shapes of billions of galaxies, and the subtle distortions in those shapes will reveal where dark matter lurks in unprecedented detail. The first major data release from the Rubin Observatory is expected in early 2026, and it will immediately become the most detailed dark matter map ever created. What these 3 instruments will produce, taken together, is something that has never existed before in the history of science. A time-lapse movie of dark matter structure evolving across cosmic history, from the lumpy early universe that James Webb is now revealing to the smooth, expansive web of filaments and voids that surrounds us today. The resolution of that movie will increase sharply over the next 6 years. By 2031, when the Rubin Observatory completes its first multi-year survey and the Euclid mission has finished its sky scan, astronomers will have precise dark matter maps for millions of galaxies, each one a single frame in a film that shows the invisible scaffolding of the universe evolving in real time across billions of years. There is a deeper question that remains unanswered, and that may not be answered for years or even decades. What is dark matter actually made of? James Webb can see its gravitational effects with extraordinary clarity, but it cannot tell us what the particles are. The leading candidates include weakly interacting massive particles, usually called WIMPs, and a much lighter class of hypothetical particles called axions. Experiments deep underground, like the Lux Zeppelin detector operating a mile beneath the Black Hills of South Dakota, are searching for WIMPs by waiting for one to collide with a xenon atom inside a tank of ultra-pure liquid xenon. Other experiments are looking for axions using strong magnetic fields and sensitive microwave detectors. So far, despite years of searching, nothing definitive has been found. But the situation is not as stuck as it might sound from the outside. Every new structural detail that James Webb provides constrains the possible properties of the dark matter particles. If the early universe was lumpy rather than smooth, that rules out certain types of dark matter particles that would have smoothed things out through their own motion. If rotation curves were already flat 10 billion years ago, that limits how warm or how fast-moving the dark matter particles could have been in the early universe. Each new observation from James Webb narrows the window of possibilities. Each new map tightens the constraints on what the particles can and cannot be. The research community has begun coordinating its efforts in new ways. The Dark Energy Survey, running since 2013, is now sharing its ground-based lensing data directly with James Webb teams, so the two datasets can be cross-checked. What is emerging is not a single breakthrough, but a network of overlapping measurements, each one reinforcing the others. Think about it in terms of your own morning routine. The coffee in your cup, the phone in your hand, the chair you sit in. All of that ordinary matter is the minority stakeholder in a universe where dark matter holds the controlling interest. Every atom in your body was forged inside a star that formed inside a dark matter halo, and without that halo, that star would never have been born, and those atoms would never have existed. You are not just made of star stuff, as the saying goes. You are made of dark matter organized star stuff, and the difference matters. The next time you step outside on a clear night and look up at the stars, try to hold two ideas in your head at the same time. The stars and galaxies you can see are beautiful and real, but they are only the foam on top of a deep, dark ocean that you cannot see, but that is there nonetheless, pulling and shaping and holding everything in place. The foam is what gets all the attention. The ocean is what actually matters. Sometime in the next 5 years, a detector deep underground or a telescope in space or an observatory on a Chilean mountaintop is going to record a signal that does not match any known particle or any known physical effect. It will be small. It might be a single flash of light in a tank of liquid xenon beneath the Black Hills of South Dakota. It might be a tiny distortion in the shape of a distant galaxy captured by the Rubin Observatory. It might be a faint glow at a wavelength that no one was specifically looking for, appearing in James Webb data as a faint line in a spectrum that a graduate student notices at 2 in the morning while the rest of the building is dark and quiet. When that signal appears, it will not look like much on its own. A single pixel out of place, a blip in a dataset with billions of points. But the people watching for it will know what it means, because James Webb and Vera Rubin will have already told them where to look. The signal will be the first direct detection of a dark matter particle, and the moment it is confirmed, every textbook on Earth will need to be rewritten.